Hello everyone. In this video I would like to show you how to build a prototype of a very simple method solver for 3x3x3 Rubik's Cube using kubesolver as a cube solving engine. So it would work similarly for Linux or Windows, but I will be showing how to do it on Linux, which I'm actually using inside of my Windows in WSL. Okay, so the first thing would be to go to the web page github.com kuba97521 kubesolver and download the code. Okay, so here we go. We clone kubesolver, we go inside. Here is the product. Like, it's on Linux, it's very easy to just build it from sources. So you can use make. On Windows, you can just download the executable. And now we will actually write our simple method solver. So I already did it, but the code is really super short and straightforward. So I will just run you through it. So first of all, so maybe before I show the code, like, how does the kubesolver work? So kubesolver is a very simple command line interface solver, which works in a way that you can specify some sequence. You won't say that I want an answer, and you can ask the solver to solve the cube. So you see that, for example, RUR can be solved in 3 moves by using R', U', R. And we can also do something more complex, like, for example, let's say RUI', RUR', and we actually want it to be solved only using LUFgen. And again, set and say that's 2 and solve. And we here see the solver found 2 solutions to RUR' insertion without using R moves, only using LUF. So that's pretty much the solver. It has some more commands which also allow you to solve only some subset of pieces on the cube. And I will show how it works by going through the code. So I wrote a very simple solver for a very bad method in Python. So let's open Visual Studio in here. I will create bad solver pi in here. Okay, it's here. We have bad solver pi, and I will be cloning code in here from my other solution. So first of all, we need some wrapper to run the solver itself, and this is pretty much very easy, and the code looks like that, so you can just copy it to your project. So ask solver once, and we can, for example, do this. We can make this code to do the stuff I showed you before. Like, we can say RUR', setgen on 1, set n1, and solve. And we can print this response, and we will see what will happen. Yeah, so we can see this is how you run the solver from Python. So this is relatively simple. And then we will go to the creation of the method. So the solver I wrote was like very crude. So basically we will have a variable that has some scramble I took from CS timer. And then we can define our method. So in the very simplest case, this is how a definition of a method can look like. So in kubesolver, you can have stuff like saying add edge or add corner. And how does it work? So for example, we can run kubesolver here again, and we can say that we want to init empty cube, and we want to solve corner. So for example, we want to solve dr, dl, df, and db edge. So I put it here. We want only one solution, and we run solve. And is it really that simple? Oh, it's an empty cube. I forgot to copy the scramble. So init empty cube. So first we need to initialize our cube. Then we can take a scramble. We can say we want only one solution, and then we can solve it, and we see 6 smooth solutions. So now we can go, for example, to alg-cubing.net and verify that for this scramble, this sequence is really solving across. Yes. So that's how it works. And the commands we have is add edge, add corner, add edges orientation, and add corners orientation. So the way it works in kubesolver is that it either solves full pieces, or it can also solve only orientation. But due to implementation details, you're not able to say, for example, to solve only edge orientation of edges in the, for example, middle layer. So that's why you cannot say just orient some edges. So that's a limitation. But other than that, here I have created like a list of steps in a very simple method where we first solve cross by adding 4 edges. And here is the gen for it. So for the cross, we want to have all possible moves. Then we're solving down, left, back corner. So we do some simple layer by layer solving. Down, right, back solver. And this we want to solve only with RLUF. Then we solve last 2 corners at the front together with RLUF. Then F2L we solve by first solving 2 edges at the back, then solving 2 edges at the front. Then we solve edge orientation with RUF, then corner orientation with RU, then CP and EP. So now, once we have defined steps like that, we will write a code for the solver to generate it. So the way we will do it, we will be simply running the solver first by giving it a scramble and asking to solve these steps using this gen. Once we have a solution for that, we will extend the scramble by the solution, add 1 more corner to pieces we want to solve. We will use this gen and repeat the process. So I already wrote a code for that. Maybe we can write it again from scratch. So basically what we're gonna do, we will say that for each and each item in the steps is step and generation in steps, and step is the first item and gen is the second item. Where is copilot? I don't have a copilot here, damn it. Step gen 1. And then we will try to remember the state of the cube. So state of the cube at the beginning consists of init empty cube. So we want none of the pieces to be solved, and we will say that. So when we encounter the first step, we want to add these elements to state of the cube. State of the cube equals or plus equals step. Okay. And then what will be the commands that we will send to the solver? So we will have to first send the state of the cube. Okay, so first we want to send this R, and then like that. Is that how it works in Python? Let's try. No, that's not how it works. Is it f string in Python? Yes, it's empty string. Okay, so we will have, like, this will be our first step, this will be our second step, third step, etc. So now, after we have state of the cube, we want to say the scramble insofar. Okay. Then we want to say that we want only one solution, and the generation should be generation for the step. Then we want it to solve, and then we will step solution equals ask solver 1 is for this command, and the result, we can print the result, or yeah, the result is called here a step solution, and we will have to extend our scramble with step solution, so that the next step will be using the scramble. So we can first print the original scramble at the top, and then try to solve. And if I did not do any stupid bug, but I did. Okay, I did some bug. So if I wouldn't have made any bug, then it would just print. I will print this command and yeah, just debug what the hell I did wrong. So we have this init empty. Okay, so the first step of the cross has worked fine. It returned the cross, and the second step did not work that fine. Okay, I see, because I did not add a space after here. Yeah, and so let's just pad it with spaces and now try to run it again. Okay, it seems it did produce something, so I will now remove this debug print and run it again. And we have some solution, and we will see if this is the solution for this method. Or let's actually take a completely new scramble. Just to not cherry pick one particular scramble. Okay, we can again run the solver. We can copy that into here. Okay, and now we have this is the scramble, and then so this should solve the cross. That's what it is. This should solve the back left slot. This should solve the back right slot. This should solve two front slots of the last layer. Then this part should solve the two back edges of F2L, and this should solve the two front edges of F2L. Then EO, CO, CP, and EP. Okay, so it seems like it's working. So basically, I think you can use this kind of code as a starter for writing any method solver that can be solved within the abstractions offered by kubesolver. And now there is, of course, a lot of potential work. So for example, if you would like to implement CFOP here, you might want to try different order of slot insertions. Or you can generate more than one solution for each step, and then kind of backtracking which of those can give you better solution for the later steps, aka zeroing. So given all of that, I think this can be used as a very, very basic start for the complex method solver for some other methods. Okay, I hope it was useful, and thanks for watching.